back at it again with 6.1. This time we're talking about area between two implicit curves. The objective of this video is to extend the area between two curves construction to curves defined as functions of y. So here I have a graph of an example where we have two curves that are not defined by functions of x, they're defined by functions of y. So that's why we write them as x equals f of y, x equals g of y. And they may be bounded by, this area that we're talking about, this may be bounded by, instead of left and right endpoints, we're talking about upper and lower endpoints. So slightly different. It may help if you tilt your view and look at things sideways. So rather than looking at it from this angle, turn your screen 90 degrees counterclockwise, and so it'll look like a regular pair of curves where C and D are now lying flat on the ground. So the idea here is, if we want to extend this concept, let's think about what our infinitesimal should look like. Rather than having vertical slices, we're going to take horizontal slices, something like this, okay? And so to see what we're talking about here, right? Let's think about what we're doing. What is the sum? So we're adding up things that look like the areas of these infinitesimally thin rectangles. So the area of the infinitesimally thin rectangle is going to look something like, we want this this width to be positive always. So we're going to do g of y minus f of y times dy. So this height dy and the width is the difference between the two curves. Okay, so it looks fundamentally the same, except now we're talking about a variable y. So really, the area will be the integral from y equals c to y equals d. I'm just writing out explicitly what the limits of integration are, because this is the first time that we're explicitly integrating with respect to a different variable, okay? So the rightmost, here's my observation that I want you to take away. The rightmost curve becomes the upper curve, okay? So here I have it written out where I identified g of y minus f of y, okay? So when we're doing the examples, when you're doing the integration, remember that the rightmost curve is going to be the upper curve, all right? So let's see an example now. And this is another basic example. So we're going to find the area, or I should say determine the area of the region bounded by two curves here. And these curves now are not, they're not going to be functions of x, they're functions of y, so they look like x equals y squared minus y minus 6, and x equals 2y plus 4. So to handle this, you're free to use some technology. Use Desmos or your graphing calculator if you want to, but I want to show you that it's actually not too hard to do this by hand. So I'm going to set up the graph here. It'll look something like this. All right. And then I'm going to go by, let's see, I think by fours. So 4, 8, 12, 16, something like that. Actually, I can do a little bit wider. Oh, 16. That should do it. And then -1, -2. And up here, I can do 1, 2, 3, 4, 5. And then I've got -4 here. Okay, so the scale, make it fit for you, but your graphing calculator, you might see a slightly different approach here. So the first one, or x equals 2y plus 4, you're always welcome to convert that into, so you can take this curve, right? And we're going to write it in terms of what y as a function of x. Sometimes that is possible, sometimes it's not, okay? So in this case, you can recognize immediately that this is a line because the function is linear in y. So x plus 2y plus 4 will turn into 2y equals x minus 4, which is y equals 1/2 x minus 2. Okay, so that curve is going to pass through these points. So this is x equals 2y plus 4. As for the other one, now you'll notice that that's quadratic in y. And so x equals y squared minus y minus 6. Maybe it's possible to factor this. So this is going to be y minus 3y plus 2, which means it crosses the y-axis at -2 and +3. Pass these through these points, okay? And it should have some vertex somewhere right in between those 2 points. So it should look something like this. Oh, whoops. Let's undo that. Let's do that again. Something like this. Not the greatest picture overall. And lastly, I need to set up my infinitesimal. So I'm looking at the region bounded between these two curves. And because I need them in terms of y, then I need to find the left and the right endpoints, which are going to be values of y. So I have a candidate here already. I have -2, because both of these pass through that point. And then there's another point somewhere over here, but I don't know what the y values of that are. So I'm going to do is I'm going to find the points of intersection. So here we go. Points of intersection. So I'm going to set g of y equal to f of y, which means I have 2y plus 4 equals y squared minus y minus 6. This is a polynomial equation. We should get some quadratic on the right-hand side here after we collect like terms and factor if possible. It is possible in this case, so I get y plus 2, y minus 5. And that actually is great because that tells us immediately that y equals -2 or it equals 5. And those are exactly the points of intersection. So those are the y values that we're interested in, which means if you go back and if you look at the infinitesimally thin slice, we're taking this thing to the infinitesimally thin slice, which I'm going to start abbreviating dA, is going to be the upper curve, which is the 2y plus 4, minus the lower curve, which is the quadratic one, the y squared minus y minus 6, dy. And we're going to take that and we're going to integrate that from -2 to 5. So the area is going to be the integral from -2 to 5 of 2y plus 4 minus y squared minus y minus 6 dy. Simplify that, but the nice thing here is, of course, this is going to turn into a polynomial regardless. So in fact, I believe it'll be negative y squared plus 3y plus 10 dy. And then when you integrate that, you're going to get negative y cubed over 3. Hope that's right. Yeah, we're on the right track. Plus 3y over 2 plus 10y. And our limits of integration, of course, are from negative 2 to 5. And now we plug in, simplify this. You can skip ahead or do this on your own if you'd like to. This is for the sake of completeness. I'm going to finish out this problem. So minus 125 over 3 plus 15 over 2 plus 50 minus negative 2 cubed over 3 plus 3 times negative 2 over 2 plus 10 times negative 2. And when you simplify that, you're welcome to skip some steps here and there. But for instance, you can combine all the fractions over 3, the fractions over 2, and then the whole numbers. So this will end up being negative 133 over 3 plus 21 over 2 plus 70. And if we get a common denominator, this will become negative 266 plus 63 plus 420. Don't say a word, not a thing, over 6. And then combine the numerator, 217 over 6, which is positive, which means we did this right. Okay, that's our answer. So I said this is a basic example just because we have already done this. Whoops. Let me just undo that. There we go. And so now let's do another example, which is going to be a little bit like the like one that we've done before. Okay. And then this example, we're again going to have to set up two integrals. Okay. So here we go. Two integrals with a z. How about that? We're going to determine the area of the region bounded by. You may have noticed all the questions here begin with, find the area of the region bounded by. Yeah, it's all the same. So this is your giveaway that this is exactly what we're looking for. So it's going to be bounded by x equals e to the 1 plus 2y. X equals e to the 1 minus y. Y equals negative 2. And y equals 1. All right. So I'm going to, again, draw the picture. You are welcome to use Desmos to help you guide this. And again, I'm going to rescale this one so that it can all fit on one page, because otherwise it'll be kind of unwieldy. Okay. And so the scale here, I'm going to go, here's 1, here's negative 1, here's negative 2. And I'm going to go by 5s here. 10, 15, 20, 25. That's because if we're dealing with something that's exponential, you can solve actually for y if you want to in both of them. Or you can think about, just think about what this would be as a function of y, and look at it sideways, okay? So whatever strategy you use, you should get something that looks like, if you plug in 0 for y, you get e. So it would cross e somewhere over here. Okay, and it crosses the x-axis at some point and then comes back down. So it looks something like this. And then the other curve will look something like this. All right, and so because we're bounded between -2 and 1, we have then two, so we have our left and our right endpoint. This, by the way, is x equals e to the 1 plus 2y, and this is x equals e to the 1 minus y, and we have to set up two infinitesimal slices because they're going to flip on us, right? Which one's the rightmost curve at that given point? So I'm talking about, we have A1 here and A2 here, or whichever one you want to label A1 and A2. But we also need to find the point of intersection, which we suspect is 0. So the y value there is going to be 0, but we should check, okay? So our point of intersection, we set the two curves equal to each other. So e to the 1 plus 2y is equal to e to the 1 minus y, which means if you take the ln of both sides, the natural log, that'll preserve the equation, and it'll just bring the powers down, so you just end up with 1 plus 2y equals 1 minus y, and then solve for y, you get 2y equals negative y, which just means y equals 0. Okay, so our suspicion was correct. And let's think then about the two infinitesimal areas that we're looking at. So dA2, our rightmost curve is the e to the minus y. So it's going to be e to the 1 minus y minus e to the 1 plus 2y dy. And for dA1, it's backwards. So we're going to flip the order of the curve. So e to the 1 plus 2y minus e to the 1 minus y dy. So is that clear? So because which one is going to be the upper curve depends on, here it's this part that we're looking at here is the upper curve, and that corresponds to the e to the 1 plus 2y. And on this side, it's the other one that becomes the upper curve. So we're really just looking at what's the area between these. So these are the areas that we're talking, sorry, not there. These are the areas that we're talking about. Looks kind of like a butterfly-ish region, yeah? All right, so our integral for area is going to be a equals the integral from -2 to 0 of e to the 1 minus y minus e to the 1 plus 2y dy plus the integral from 0 to 1 of e to the 1 plus 2y minus e to the 1 minus y dy. Just one problem here, though. We need to figure out some antiderivatives first, some indefinite integrals, okay? So first of all, some scratch work. First of all, what's the integral of e to the 1 minus y dy, okay? And we're going to not focus on the limits of integration because that's going to change, but the important observation here to use is we can use the substitution rule. which says if we let u equals 1 minus y, so this is this new variable u, then du will be negative dy by taking the derivative of u, which means if we plug this back in, this integral is going to become integral of e to the u times negative du. And when we do that, that will turn into, I'm going to need another page, equals negative integral of e to the u du. And this is just the direct application of that exponential rule. So it's going to be negative e to the u plus c, whatever c is. We're not going to worry about that really. But remember that u, we're going to have to replace that back. So that's negative e to the 1 minus y plus c, whatever that happens to be. Same thing for the other one. So also the integral of e to the 1 plus 2y dy, that suggests we're going to use u equals 1 plus 2y as a substitution. I'm using u again because we already finished the other substitution, but if you're uncomfortable using u again, you can use v. So this will be du is going to be 2 dy, again, by deriving. And so that means that this integral is going to become the integral of e to the u times 1/2 du, because if you want to isolate dy, you have to divide both sides by 2. And so this becomes 1/2 integral of e to the u du, which will be 1/2 e to the u plus, call that some other constant, call that d, capital D. And then you just plug in the u back. So it's going to be 1/2 e to the 1 plus 2y plus capital D. Okay, so this is the important part here. When you integrate this, it becomes this. And when you integrate, oh, no, not that, sorry. This, it becomes this, okay? So not too bad. All right, back to it. So remember, we were working with this nasty integral. Now there's a lot going on here, but fundamentally what we're doing is we're just going to replace each one by its antiderivative, which we already did. We just need to place the correct one in its spot, and then we're going to use the correct replacement of the limits of integration. We do not need c and d that we just found. We don't need those. Those are unnecessary. So a is going to be negative e to the 1 minus y, because that's the integral of e to the 1 minus I, minus 1/2 e to the 1 plus 2y from -2 to 0, plus 1/2 e to the 1 plus 2y minus, plus e to the 1 minus I, because the negatives cancel, and that's from 0 to 1. Okay, and then you plug in your limits of integration, you're going to get a whole nasty mess. I'll go ahead and do that work here, but you can skip ahead or work this out on your own if you want to. It's just some tedious algebra, but we're using FTC2 to get negative e minus 1/2 e, close parentheses, minus negative e cubed minus 1/2 e to the -3 plus 1/2 e cubed plus e to the 0 minus 1/2 e plus e. Not too bad. And if you collect like terms, notice that there are just single powers of e. Treat that as its own variable. E to the 0 becomes 1. And then there's an e cubed in here twice, and an e to the negative cube. So there should be four distinct terms in this expression. And I'm going to order them from highest power of e to least power of e. So really it's a polynomial in e. So 3/2 e cubed minus 3e plus 1 plus 1/2 e to the negative 3. And that's our answer. So as you can see, the calculations themselves, they can be more onerous than the actual calculus involved, right? But that's all really we need to know here. We will be using this tool later on, especially as we try to figure out connecting area to volume. So just as we took these infinitely thin slices that were just basically just little sticks, right? These little infinitely thin lines and adding them up to make area, we're going to do something similar in the next few videos where we're taking infinitely thin slices, which are little areas, and adding